Okay, so we're back in class 15, and here's another example, a little bit longer. This one uses 3 pi terms for Buckingham pi, and this is problem 714 out of Munson's book. It's a great book, you should buy it. Assume that the flow rate, Q, of a gas from a smokestack is a function of the density of the ambient air, the density of the gas within the stack, the acceleration of gravity, and the height and diameter of the stack. Use the density of the air, the diameter of stack, and the acceleration of gravity as repeating variables to develop a set of pi terms that could be used to describe the problem. All right, so we're going to apply Buckingham pi to this scenario right here. Let's take a look at that. Boom. Okay. So if we follow the step-by-step method I had described in class or in the previous video, we're going to first write out what our function is, right? So they're saying that the flow rate is a function of the density of the air, the density of the gas, the acceleration of gravity, and the height and diameter of the stack. So that's 1, 2, 3, 4, 5, 6 variables. Now, I like to write these out right away, so I'm thinking about them. You can see that the dimensions of Q is going to be L3 T negative 1, because it's going to be like cubic feet per second, cubic meters per second, what have you. The densities, it could be both of them. They're both going to be. And here, I think I'm going to go with the MLT system. Because if you're looking through here, we can see really there's no terms of force in there. So FLT isn't useful. So we will use a much easier MLT to represent the density. So that's going to be M and L minus 3, because that would be like kilograms per cubic meter, slugs per cubic foot, that kind of thing. Acceleration of gravity, length and T minus 2, because it'd be feet per second squared or meters per second squared. And then lastly, H and D, they're both going to be length terms. So we can see that we have length represented, we have time represented, mass represented. So we have 3 different dimensions represented. That's pretty typical. We had the previous example only had 2. There it's possible to have 4 because we might actually have temperature involved right there too. But that's the extent that we have of these. So we take our step 3 and K minus R, and we know that's going to be 6 minus 3. So therefore, what we've decided, we have 3 pi terms. 3 pi terms. Step 4 has been kind of done for us in the problem statement because they said to use these as the repeating pi terms. If we didn't have those, we could kind of like think our way through them. We might have chosen other things than this, but what we would not have chosen, we wouldn't have chosen 2 of the densities, right? Because they've already represented one of the. So we might go the density of the gas instead of the air. We wouldn't have chosen both H and D because we already have like a length represented by either one of them. But we could have chosen a height, maybe. Acceleration of gravity is a good one to pick because it incorporates some time in there. And we noticed that time wasn't represented by either one of these. So those are kind of like sort of the general ideas behind what if you had to pick them yourself. And there's nothing magic about picking one or the other. It's just, you might run the experiment and discover that it didn't, when doing this dimensionless group, it didn't behave like you with something consistent or something that would be allow you to use that data again, right? So you would, maybe you would mix it up and try to see which of these, whether the density of the gas or the height of the stack would be the better parameters to use for the dimensionless group. So we go to 5, and I'm going to use a lot of paper here. And this is our main step. where we take our first pi term, pi 1, and we're going to say that it's going to be q times the repeating variables raised to an index, raised to a exponent, excuse me, not index, a exponent. It's the opposite, right? Superscript, not subscript. And we have, I wrote it in my papers with G, so it doesn't matter what order I put them in, but just to make it my life easier, I'm going to pick consistency. And then lastly, we're going to have D raised to the C. So our job, our mission in this Buckingham pi, which is really just to try to do kind of exponent math, to try to figure out what combination of A, B, and C, when we put onto here, combined with this Q on all these variables, will give us a dimensionless result. So underneath this, I'm going to put what actually, let me, I should have done this in class when I did this, but get my quality Westcott B55, sometimes referred to as the see-through, handy dandy ruler here, and I'm going to make some nice columns. I think I did this by hand in class when doing it, but the neatness counts, right? So I'm going to put a row underneath that, and I'll write up my L3 T minus 1. And then for here, I'm going to put my ML minus 3 to the A. Here I'll write my LT minus 2 to the B. And here I'll write my L to the C. Let me extend this further a little bit. And my goal is to get M to be 0, L to be 0, and T to be 0. So underneath, I'm going to make 3 rows. I'm doing a great job keeping that thing straight, didn't I? And over to here. And I guess I'll close that down. Might as well make it neat. Huh? And do it. M. Oops. Not there. Over here. M, L, T. Right? And so I'm just going to go across one at a time. I start with M. There's 0 right here. There's M. I have an A. This M is raised to the A, so we're only going to write down the exponents. I go to the next one over, and there's no M there. No M here. And this should be equal to 0. So we could do this afterwards, but let's go ahead and recognize that this is an equation where we add all these things together, and then they equal 0. So we note that A is equal to 0. We'll try the L now. All right, so now we're actually working with something here. We've got 3. Now we take M to the A. Right, so there's going to be an A, negative 3. Negative 3A right there, right? And negative 3A. And then we're going to have it to the B, okay? And we're going to have it to the C. That's going to be equal to 0, right? So we could write out our equation here. We're going to say that 3 minus 3A plus B plus C is equal to 0. But we already knew that's going to be equal to 0. Right? So we have an equation that says 3 plus B plus C is equal to 0. We still don't know. So let's hope that whatever happens here is going to be able to resolve and get us the C so we can find out the B. So we start up to here, and we see for time, we have a negative 1 here. 0 there. We're going to have a negative 2b and 0 here, and we want it to equal to 0. So then with that equation, we're going to say that, well, okay, negative 1 minus 2b is equal to 0. Therefore, that b is equal to negative 1/2, right? Because you're going to bring this over to the other side. Yeah. So knowing that, we can come back up and put this back into here. And we can see that what we're going to end up with, if we do the math ourselves, we'd have a 3 plus our negative 1/2 plus c is equal to 0. Therefore, c has to be a negative 5/2. Trying to understand what to do with that, we come back up to this pi term, and we say that the first pi is going to be q times density raised to the 0, and then g raised to the negative 1/2, and then d raised to the negative 5/2. So pi 1 is going to be q divided by the square root of g d to the 5. That becomes our first pi term for this. Not one we would have predicted, probably, right? Now, moving on to the next one. So I included 2 sheets for the note sheets here in this. We're going to go step 5. Step 6 is to do it for the other variables, right? So the other non-repeating, right? So these were the repeating variables. We were given that, right? We said that we're going to have these right here. So we've covered this one. We're using that as a repeating variable, and that as a repeating variable, and that. So the non-repeating ones, excuse me, I should have. This is a non-repeating, and this is a non-repeating, so we have to do the Buckingham pi for this one and for this one. The truth is, though, these are going to be pretty obvious because we can just take a ratio of these two parameters. So let's do the second one, and maybe because we are on a video, we could just go ahead and make it a longer video and do all of them. Anyway, we're going to say that's going to be equal to the density of the gas, because that's the non-repeating was the gas. Repeating was the air. And then we're going to times the density of the air raised to the A, the acceleration of gravity raised to the B, and the diameter raised to the C. And I don't know how long the columns need to be. Something along those lines right there. Underneath this, I'm going to write what the density is going to be is ml minus 3. Here it's going to have ml minus 3 to the A. And here you're going to have lt minus 2 to the B. And here's going to be L to the C. And that's going to we want the equaling M0, L0, T0. And so we'll make 3 rows underneath this. Oops. And clean it up a little bit. Didn't do a great job with that last row. It's not as neat as I could make it, but it's good enough. And so we have M, L, and T, and we proceed here. So first off, we see M1. Here we get A. 0, 0 equals 0. So right away we see 1 plus A equals 0. Therefore, A is equal to negative 1. That was kind of obvious, right? That we're going to have a ratio of these two things is going to be our pi term. But let's see how the rest of it works out here. L, we have a minus 3. Here we're going to have a minus 3A. Here we're going to have a B. And here we're going to have a C. Is that true? I think so. So we're going to have an equation that's negative 3 minus 3A, which, by the way, we know is negative 1, so that's going to cancel out that 3, right? plus B plus C equals 0. We can already cancel this out because we're going to say there's going to be a positive 3 in there because of that. All right, so this last one, we'll see there's a 0 time, negative 2B, 0 time equals 0. Therefore, negative 2B is equal to 0. B is equal to 0. Boom. Therefore, C must be equal to 0. I don't know a more convenient way to write this out, but this just demonstrates that I've thought my way through this thing, right? You know, maybe sometimes I like write that right there. I don't know if someone reading this could follow what that says. But anyway, what we're left with, and when we write back up at the top, we guess that a pi 2 is going to be equal to density of the gas times the density of the air to the negative 1, right? And gravity to the 0, diameter to the 0. Therefore, our pi 2 term is going to be density of the gas divided by the density of the air. I'm already at the 16-minute mark, so I don't know if I want to continue any further. I did work it out for the other one. I could write this down that the third pi term is definitely going to be the other repeating ones. So the non-repeating one was h divided by the diameter. Yes, that too is a ratio. Would come out if you didn't believe me. Here it is, me doing it out. You can see that the mass, right, there's 0 here, but there was mass down there, and A is equal to 0. Length right here, you can see we have a 1, negative 3A, but this was already 0, B plus C right there. But then this last one, you can see once again that the B is going to be 0, so we end up finding that C is a negative 1, which was just going to make sense all the way. So you can see that we did have that carry through. For our last, so that was step 6. For our last one, we really should double check our our pi terms dimensionality, especially the first pi term because it's a weird one where we had Q divided by square root of G d to the 5th. If we were to, let's put these in there just as a double triple check. We are going to have G square root of it, right? So it's going to be L to the 1/2. Now I don't like doing it that way. Let me keep this way. I don't know. We go L and then T minus 2 and then L5, but all raised to the 1/2. So if you distribute that 1/2 up and you raise everybody back up to the top, I think this is a better way to double look at the thing. You're going to have a negative 1/2 right there because that guy right there, but he went up to the top. The T is actually going to be just a regular T, right? Because it went to the top, so the negative went away, and it was square rooted, so the 2 went away. And then lastly, you're going to have L to the negative 5/2 right there, right? So this is just a double check on there, and it's not. I'm getting tired already. It's early. It's only 12 o'clock. So anyway, we get the T's cancel out, and then here that negative 1/2 and then negative 5/2. That's going to turn into a 3. Yes, those cancel out. So that's our check. And then lastly, let's write out what our statement here. And we're really saying this pi term is a function of these 2 pi terms. And in the next class, we will see, I did this again, I did that in class too. We will see that there's sort of the law of models or rule of models. I'm trying to remember, is it rule or is it law? Anyway, that says if you want to like do some type of experiment with a model, you need to have this in agreement and this in agreement. When that happens, then you're allowed to have that in agreement. So that's one of the reasons why we're writing out this statement. 20-minute video, longer than I liked, but this is a longer process than the previous one. Maybe I'll make another video for this. I don't know. I'll decide in a minute.